let's get into the calculation a little bit. After all our fun with finding out intuitively where the average is, now we have to push the pencil, but not very hard. You remember the number of trials was n, and the p was the underlying probability. Well, we're going to select 12 jurors, so the number of trials is going to be 12. And this is on slide 8. The underlying probability, I think I said just a couple minutes ago, was 0.8. So the average x bar is equal to the number of trials times the probability, or 12 times 8, or 9.6. So if you look back at slide 7 and remember, or you have that sitting out where you can put your finger underneath there for a balance point, it's going to be right about at 9.6. And you can impress your friends and I know you're thinking, I can't wait to tell people about this. Contain yourself. There's more fun to be had here. Now we need, what do we need to talk about usual and unusual values? We need a standard deviation estimate. So let's do a standard deviation estimate. And the standard deviation is equal to n times p times q. And remember, we defined these earlier. N's the number of trials, p's the underlying probability of success, and q is 0.2. I just realized, as I said that the standard deviation is equal to the square root of n times p times q. So don't forget to take the square root of that, because that really calculates something a little bit different and you'll get a funny answer. But I do have a square root sign on slide 8, and what it comes out to be is equal to the square root of 1.92, or equal to 1.385, which we can round up to 1.4. So the standard deviation is going to be 1.4. So now we can go back and use our identifying on slide 9, identifying unusual results with the range rule of thumb. What are we going to do to identify unusual results? We're going to take the average, 9.6, plus 2 times 1.4, and the average 9.6 minus 2 times 1.4. And that's going to give us our window of usual selection numbers that we should see if these trials of 80% are being consistently demonstrated in our sample without bias. So we go to slide 10 and I finish that calculation off. So we go to 12.4 and down to 6.8. So what that says, let's take a look at slide 11 and go back to our histogram and see what this tells us. We got our frequency histogram here. And 10 was the tallest bar, 11, 12, 9, 8, 7, 6. Okay, there's a couple of blue arrows coming down on slide 11, and one comes down and points just past the 12, or at 12.4, and one comes down at 6.8, and it said, what that says is You remember what it says? Ask your friends, ask one of your friends in the room. I know the room's filling up with relatives, friends, all kinds of people have come by and said, boy, this looks like fun to me. 95% of our jury selections should fall within 6.8 jurors, or 7 if you round it up to whole numbers, and up to 12 jurors. So 95% of the time we should have 7, 8, 9, 10, 11, or 12 jurors, and we would not be in an unusual bias of favoritism to select too many Mexican American jurors if we were 12 or less, and if we're 7 or more, we wouldn't be accused of bias of not selecting enough Mexican American jurors. So how neat is that? If we, well, we'll go into a couple more, we'll talk about this a little more in the next section, but I wanted to demonstrate to you the notation, the use of the usual and unusual values, average plus 2 standard deviation minus 2 standard deviation, be able to calculate those using N, P, and Q for the average, N times P, and the standard deviation, N times P times Q, and remember to take the square root, because someone didn't a little bit earlier, but I saw it in time. And then you just add plus 2 standard deviation, minus 2 standard deviation. You can say, are we, what can we expect to see as far as our success rate, given what we're seeing right now? Our success rate of in an unbiased way, selecting jurors. This could have been patient admittance, you know, any number of counting instances. So we'll come back, go over a few more slides, and conclude. Take care.